1101, Chapter 2, examples. So I'll do a few examples here in a little brief time. And what I'll do is explain some. These are from the text. Again, this is the 7th edition. I'll go point out the problems. I'll show you pictures of them, and then I'll work them out. So if you don't happen to have the book, that's fine. So here's the first one. And you can stop and look at it. Okay, a car travels along the x-axis with increasing speed. We don't know if it's going to the left or right, which means positive or negative. Which figure below best represents the motion of the car? So that's A, that's B, that's C, that's D, and that's F. All right? So increasing speed. So what we mean by increasing speed is that if we plot the graph of x versus t, say a falling object, now let's say x versus t. If an object is not moving at all, it's going to do something like that, right? If it's moving with constant velocity, it'll be doing something like that, right? Now, if it's accelerating like an object in free fall, so if I just drop it, what does it do? Remember, acceleration. If it's falling, we can use y is 1/2 gt squared, so it goes as the square of the time. We just drop it from rest, start from 0. If we plot y instead of x, doesn't matter, but then what you're going to have there is a graph doing that, all right? As far as, so that's the parabola. So from that, you might be able to figure out which one of those 5 graphs would actually represent increasing speed. Increasing speed can be both positive or negative. Right? If it's falling, it's increasing speed, becoming more and more negative. In this case, I'm having it increasing more and more positive, but you can see what that would be. So that should help you with that. That's misconception number 9. So you can get the answer, figure out that one. Okay. That's the first example. I'll do about 4 altogether. All right, the next one is, this is from section 2.4. Let's back. Okay, a sprinter accelerates from rest to 9 meters per second in 1.38 seconds. What is their acceleration in meters per second? I'm not going to worry about kilometers per hour. That's irrelevant for this particular problem. So there's the problem. It's number 18 in section 2.4 in problems. And I'll write down what we have here. So, goes from rest. So V naught is 0. And V final, V is 9 meters per second squared. 9 meters per second. And time is 1.38 seconds. All right, so what we want to do is find the acceleration. All right, we go back to our equations, and what do we know here? What are we trying to find out? All right, we're given a velocity, we're given initial velocity, final velocity, a time, and we want to find the acceleration. In this case, the distance is irrelevant. I mean, I can ask that too, is that based on question, I could then ask how far does it actually go? I mean, that's part B of this question if I want to ask that. How far does she actually travel that distance? Well, the first question, we'll go back to our equations of motion for here. And what we're going to use is the first one. V is V naught plus A times T. All right, because in this case, we're given the initial velocity, final velocity, and the time. So it'll be, rearranging it, there'll be V minus V naught divided by time is A, which would be 9 minus 0 over 1.38, which, if I figure, look at that, 9 divided by 1.38 is approximately 6.52 seconds. 6.52 meters per second squared. All right? So that would be acceleration, which is pretty good. I mean, that's about 2/3 of G. So that's pretty fast. All right, during this time, the runner is constantly accelerating. How far are they going in that time? Now, there's a couple equations we could use for this. If you go back to original ones, we could either use the second equation or we could use the third equation. And actually, I will use both just to show you how this works. So the second equation, all right, so A is 6.52 seconds. So what we do is go to find X. X would be X naught, which is 0, plus V naught. T, which is also 0, plus 1/2 AT. So it's X is 1/2 AT squared, which is 1/2 times 6.52 times 1.38 all squared. So if I solve for this, 1.38 squared times 6.52 divided by 2, I get 6.21 meters, right? So that's how far she would travel using that. Now we should get the same expression using this third equation. V squared is V naught squared plus 2A delta X, or X. That's 9 squared equals 0 plus 2 times 6.52 times X. So that would be 81 over 2 times 6.52, which I get 6.21 meters. Same answer in both cases. So you can solve it either way, depending on the problem, depending on what you have for information wise. In this case, we could not have found X directly because we didn't know the acceleration. So we would have to find the acceleration before we find the distance it travels. So we have to know that. So we have to solve for the acceleration first, and then once we do that, we can use either expression to get the equation there. All right, so that's that example of 2.4 exercise then. All right, so here's another one I won't do. Is this example here is this problem section 2.5. a car slows down from 28 meters per second to rest in a distance of 88 meters. What is the acceleration? Hit. So this is again for the book, problem 22. So we have initial velocity is 28 meters per second. Final velocity is 0. And the distance it travels, delta x, or x, is 88 meters. And the question is, what is the acceleration? Well, in this case, we don't have the time, so we're not asking for the time. We could probably figure it out if we want to ask for how long it takes to do it, but in this case, we just ask for acceleration. So we're going to use the third equation. V squared is V naught squared plus 2ax. In this case, final velocity is 0. Initial velocity is 28 squared plus 2. We're trying to find a times 88. So we subtract, it's minus 28 squared over 176 multiplying 2 times 88 is a. And if we solve for that one, we get 4.45 meters per second squared, and it's negative because of the negative. So that's a deceleration in this case for this particular problem. All right, so again, that's problem 22, what just showed you there as far as that case. Okay. All right, last problem that I'll do here is problem 27. I'll show you that. Okay, problem 27. A car slows down uniformly from a speed of 28 meters per second to rest in 8 seconds. How far did it travel in that time? All right. So for this equation problem, whenever you have a problem, sketch out what you're doing, put down what you know, and then what are you trying to find out? So in this case, it travels a distance x, which is what we're trying to find out. It starts with initial speed, velocity of 28 meters per second. It slows down to rest, so V is 0 with a time of 8.0 seconds. All right, so we're trying to find the distance that it travels to do that. All right, now we're going to have, and if you look at our equations from before, all right, there's no equation where we can just stick it in one thing and solve it. All right, because we use the first, so if we use x is, V naught, x naught plus V naught t plus 1/2 at squared. Well, we don't know the acceleration. We can do that, right, because x naught is 0, V naught is 28. We know the time, but we need to find the acceleration. So we're going to have to find the acceleration, and the acceleration is going to be, back to our original prop equations, is V naught plus at. So we want to solve, we need to solve for the acceleration first, right? Because in this step, it's a two-step problem, which makes it slightly more complicated. V is 0, 28 is initial, plus a times 8. All right, so that's minus 28 over 8 is, looks like minus 3.5 meters per second squared. All right, now we have that. We can now figure out how far it's gone. All right, we're not starting from rest and going faster. We're starting from certain speed and slowing down. So we will put in x is v naught, 28 times 8 plus 1/2 times 3.5 times 8 squared. So be careful what you are using, right? It's so common to just, oh, well, we're starting from rest and accelerates, we just use this part. Well, no, that's not true. We're starting from a certain speed and slowing down. All right, so this is not 0. And that's going to be minus, so that would be x is, I'm just going to multiply these out. That's 224. And that's minus, let's see, 64 times 3.5 divided by 2. Okay. Negative 112. So that would be 112 meters. Travels. All right, so that would be the velocity. That's how far we travel in that time period. So that's kind of enough on those situations as far as examples are concerned. So that's pretty much what we'll be looking at. I've gone through some other examples. Another thing you might want to look at is the graph on 55 is problem 55 is, if you look at it, velocity of a train is a function of time. During what times is velocity constant? And what time, when is during time, is acceleration constant? Is there a time where the acceleration is 0? All right, and what is the velocity at certain times as far as what's going on? So those are some examples from chapter 2 as far as that exercise. So the first exam will be on chapters 1 and 2. So there will be a review for those. All right, so